Everything we see began with a single, unimaginable spark. But what ignited that spark? What were the very first pieces of reality? The original seeds from which every galaxy, star, and atom grew. We are about to embark on a journey through 30 of the most profound theories ever conceived about the universe's first particles. You will gain a complete map of cosmic origins, from the bedrock of established physics to the farthest shores of speculative thought. We will explore how entire universes might bubble from a quantum foam, and if the first thing to exist was not a particle but a thought, which idea about our deepest beginning feels the most true to you? The story of our beginning is often told with a single, explosive name, the Big Bang. This is our first and most fundamental theory, the cornerstone of modern cosmology. It proposes that our entire observable universe was once compressed into a single point of infinite density and temperature, a state physicists call a singularity. At this moment, time and space as we understand them simply did not exist. There was no before, no outside, and crucially, no particles in any recognizable form. Instead, all of reality was a seething, unified ocean of pure energy. The forces that govern our universe today, like gravity and electromagnetism, were fused into one superforce. In this unimaginable furnace, the ideas of here and there, or this and that, had no meaning. It was the ultimate blank slate, the original condition from which everything else would unfold. So the Big Bang singularity theory does not give us a first particle. Instead, it gives us a first state, a primordial seed of pure potential. From that seed, in the first fleeting fractions of a second, the universe underwent a rapid expansion known as inflation, stretching faster than the speed of light itself. As it expanded, it cooled, and as it cooled, that unified energy began to condense and differentiate, like water vapor freezing into intricate snowflakes. From that cooling, the first particles finally crystallized into existence. This theory sets the stage for everything to come, providing the canvas upon which all other ideas about our first particles must be painted. But a singularity is a problem in physics, a point where our equations simply break down. To understand what happened next, we need a new character in our story. Enter cosmic inflation. This theory solves a cosmic riddle: why the universe looks so remarkably uniform in every direction we look. The answer is a breathtaking expansion. In the tiniest sliver of time after the Big Bang, the universe did not just expand, it ballooned at a rate far beyond the speed of light, growing by a factor of trillions upon trillions in less than a blink. What could possibly power such an event? Physicists propose a hypothetical energy field that permeated all of space, called the inflaton field. Think of it like a cosmic engine, a pressure that pushed space itself apart with incredible force. The first particles in this view are not matter as we know it, but the quanta, the individual packets of energy of this inflaton field itself. These were the original actors on the stage, their behavior dictating the fate of everything to come. And here is the crucial part. Even in this ultra-smooth field, quantum mechanics tells us there were tiny, unavoidable ripples, random fluctuations at the smallest scales. As inflation stretched the universe, it stretched these microscopic ripples too, magnifying them to cosmic proportions. Those magnified wrinkles in the fabric of spacetime became the gravitational seeds for everything, the blueprint for all future galaxies, stars, and planets. The inflaton field did not last forever. When its job was done, this field decayed in a process called reheating. Imagine that cosmic engine sputtering and releasing all of its pent-up energy in a burst. The quanta of the inflaton field transformed, their energy flooding the universe and reheating it into that seething hot soup of fundamental particles, the quark-gluon plasma. So inflation gives us a two-step origin, a cosmic stretching that imprinted the universe with structure, followed by a grand transformation that filled it with the raw material for matter itself. The universe was now flooded with a hot, dense plasma, but we must push our inquiry back even further, to a time so early it defies our current physics. This is the Planck epoch, the first 10 to the negative 43 seconds after the initial moment. At this unimaginable scale, the universe was smaller than a single subatomic particle, and conditions were so extreme that all four fundamental forces, including gravity, were unified into one. Here, the smooth fabric of spacetime we take for granted dissolves into something far stranger. Physicists call this realm quantum foam or spacetime foam. Picture the surface of a violently boiling ocean, but instead of water, it is the very geometry of reality that is churning. At these scales, the principles of quantum mechanics and general relativity collide. Heisenberg's uncertainty principle suggests that empty space is never truly empty. It is a seething sea of virtual particles constantly flickering in and out of existence. Now magnify that idea to the ultimate extreme. In the quantum foam, spacetime itself becomes probabilistic and foamy. Tiny wormholes might form and vanish, minute tears could appear and heal, and the concepts of before and after lose all meaning. In this chaotic, frothy sea, what could be considered the first particles? They would not be particles of matter like electrons or quarks. Instead, they would be transient excitations of spacetime geometry itself, brief knots or twists in the fabric of reality bubbling up from the foam. These are not objects moving through space, they are fluctuations of space and time and gravity all woven together. Some theories even suggest that entire baby universes could spontaneously nucleate within this foam, budding off from our own cosmic lineage only to collapse or inflate away into their own separate realities. So in this view, the very first seeds of existence were not things but events, ephemeral quantum tremors in the primordial foam from which all structure would eventually crystallize. It is a vision of creation born from chaos, where the universe began not with a single bang, but with a trillion simultaneous quantum whispers. This chaotic quantum foam hints at a deeper order, a single set of rules that governed even that first flicker of existence. This brings us to our fourth profound idea, the quest for a theory of everything, and its most famous candidate, string theory. What if the most fundamental building blocks of reality are not tiny dots but tiny, vibrating strings? This is the radical proposal of string theory. It suggests that every particle we know, from quarks to photons, is not a point but an unimaginably small loop or strand of energy, vibrating at a specific frequency. Think of a guitar string. Pluck it one way and you hear a specific note. Pluck it differently and you hear another. In string theory, each distinct vibrational pattern of these fundamental strings produces a different particle. One note might be an electron, another a quark, and another the particle that carries gravity, the graviton. This elegant idea could unify all forces and all matter under one mathematical framework. So what does this mean for our very first particles? In this view, the universe's original constituents were not particles at all, but the most fundamental vibrational states of these strings. They emerged as the universe itself crystallized from a higher dimensional landscape. String theory often requires more than the three spatial dimensions we experience. Some versions propose our entire universe is a three-dimensional membrane or brain floating within a higher dimensional space. The birth of our cosmos might have been the moment this brain was created or set into motion. The first things to exist within it were the primal vibrations of strings, their notes dictating the initial conditions of everything to follow. It is a vision of creation as a cosmic symphony, with the first particles being the opening chords, played on strings a billion times smaller than an atomic nucleus. String theory paints a universe born from vibrating notes, but there is another grand vision that rewrites the very stage upon which those strings would play. Loop quantum gravity takes a radically different path. It asks a profound question: what if spacetime itself is not a smooth, continuous fabric, but is instead woven from individual threads from tiny, indivisible building blocks. This theory proposes that space has a discrete, granular structure, like a digital image made of pixels but in 3 dimensions. These fundamental units are called quanta of space or spacetime atoms. Picture the cosmos not as a blank sheet, but as an incredibly intricate, ever-evolving network of connections, a spin network where each link represents a tiny volume and each node represents a surface where space quanta intersect. In this view, the first particles of matter are not the primary reality, they are secondary. They emerge as excitations or defects within this dynamic web of space itself. An electron, for instance, could be a specific pattern of twists or knots in the spin network, moving through it like a wave travels across a net. This granularity of space provides a natural limit to how small things can get, preventing the infinities of a singularity. And this leads to one of the theory's most stunning implications for our origin story, the Big Bounce. If space is made of finite, quantized pieces, then it cannot be crushed into an infinitely dense point. Instead, as a previous universe contracted under gravity, the density of these spacetime quanta would reach a maximum, and then quantum repulsion would cause a rebound. Our Big Bang was not a beginning from nothing, but a great turning point, a moment where the spin network of a prior cosmos reached a limit and then reconfigured itself in a new expansion. The first particles in our universe, then, would be the rearranged excitations of this reborn spacetime fabric, the inherited patterns from a cosmic cycle stretching back without end. The granular tapestry of spacetime had now cooled enough for the first ingredients of matter to emerge from the energy of creation. We arrive at a moment a few microseconds after the initial spark, entering a realm both alien and familiar, the era of quark-gluon plasma. Forget any notion of atoms or even protons and neutrons. The universe was now an opaque, seething ocean, a primordial soup 10 billion degrees hot and denser than the core of any star. Within this blindingly bright broth, the fundamental building blocks of matter, quarks and gluons, roamed completely free. Quarks are the tiny, point-like particles that normally combine in threes to make protons and neutrons, while gluons are the sticky particles of the strong nuclear force that normally glue them together. But in this unimaginable heat, the glue had melted. The strong force was too weak to bind them, so quarks and gluons existed in a state of perfect liberty, a chaotic, collective fluid where no composite particle could hold itself together for even an instant. This was the universe's first and most extreme state of matter, a perfect liquid more frictionless than anything we can create. It was a cosmos you could not see through, for light was trapped, constantly scattering off this dense soup of charged particles. How can we possibly know about a state that vanished in a flash? We recreate it. In laboratories like the Large Hadron Collider, scientists slam together nuclei of heavy atoms like lead at velocities approaching the speed of light. For a fleeting moment, in the heart of those microscopic collisions, temperatures soar to trillions of degrees, and a tiny droplet of quark-gluon plasma flickers into existence. It lasts for less than a billionth of a second before cooling and condensing, allowing the quarks and gluons to finally snap together into the familiar particles we know. These experiments are our time machines, letting us probe the forces that govern the universe in its infancy. They reveal a cosmos that began not with solid things, but with a collective, fluid frenzy of ultimate freedom, a fleeting moment of pure potential where the rules for all future structure were written in fire. That fleeting moment of perfect freedom could not last. As the universe continued its relentless expansion, it cooled further, and a fundamental change swept through the primordial soup. This is the moment of hadronization, a critical phase transition where the rules of reality shifted once again. The temperature dropped below 2 trillion degrees Kelvin, a threshold where the strong nuclear force, once too weak to act, suddenly became the dominant power in the cosmos. The era of free quarks and gluons was over. Think of it like water freezing. One moment you have a liquid where molecules slide past each other freely. The next, as the temperature drops, they lock into a rigid crystalline structure. In the cooling universe, the strong force acted like an unbreakable elastic band, snapping into existence between the quarks. This is called quark confinement, a fundamental law stating that quarks can never be found alone. They are forever bound into composite particles called hadrons. As the plasma cooled, quarks and gluons rapidly found each other, combining in specific, allowed configurations. Groups of 3 quarks formed baryons, the most stable of which are the protons and neutrons that build our world today. Other combinations produced a zoo of unstable particles, but it was the protons and neutrons that survived, becoming the first stable, long-lasting pieces of matter in the universe. This was not a gentle process, but a sudden crystallization of matter from the energy of the earlier fire. The precise conditions of this transition, the exact temperature and density, dictated a crucial ratio. For every 1 neutron that formed, approximately 7 protons were created. This 7-to-1 imbalance was not a random accident. It was a direct result of the universe's expansion rate and the slight difference in mass between the up quark and the down quark. That simple numerical ratio, forged in the first few minutes, would become the master blueprint for all future chemistry. It determined how much of the universe would become hydrogen with its single proton, and how much would eventually fuse into helium and the other elements. In those critical moments, as free quarks vanished forever into protons and neutrons, the destiny of every star, planet, and molecule was quietly set in stone. Yet this creation of protons and neutrons presents us with a cosmic mystery so profound it questions our very existence. Why is there anything here at all? According to our best theories, the early universe should have created matter and its perfect mirror opposite, antimatter, in absolutely equal amounts. For every proton born, an antiproton should have been born alongside it. For every electron, a positron. And when matter meets antimatter, they annihilate in a flash of pure energy, leaving nothing behind. If the universe had been perfectly symmetrical, every particle of matter would have found its antimatter twin, and the entire cosmic experiment would have ended in a silent, featureless bath of light. There would be no stars, no planets, no us. The fact that we are here to ponder this means something tipped the scales. Some process in that first second violated the perfect symmetry and left behind a tiny, precious surplus of matter. This is the great puzzle of baryogenesis, the birth of an imbalance. How did a universe poised for total self-destruction end up with anything left over? Physicists believe the answer lies in a subtle crack in the mirror of nature, a phenomenon called charge parity violation. In simple terms, the laws of physics treat matter and antimatter almost but not quite identically. There is a tiny bias woven into the fabric of reality itself. In the extreme conditions just after the Big Bang, certain particle interactions, possibly involving very heavy, exotic particles that no longer exist, played out with this slight bias. These processes acted like a cosmic sieve, filtering out just a little more matter than antimatter. The scale of this victory was vanishingly small. For every 1 billion particles of antimatter, there were 1,000,000,001 particles of matter. That 1 part in a billion difference is all that survived the Great Annihilation. When the smoke cleared, after almost everything had cancelled itself out into radiation, that 1 in a billion surplus was left floating in the void. So the first stable, long-lasting particles, the true survivors of creation, were not the countless protons and electrons born in the plasma. They were the heartbreakingly rare excess protons and electrons, the ones who had no antimatter partner to annihilate with. Every atom in your body, every star in the night sky, is made from that 1 in a billion relic. We are not the ash of a great fire, we are the leftover crumbs from a feast that almost consumed itself entirely. That 1 in a billion victory gave us a universe of matter, but it left a glaring question unanswered. our best model of particle physics, the Standard Model, is a triumph, yet it feels incomplete. It explains the particles we see, but it cannot account for the vast, invisible scaffolding of the cosmos, dark matter. This is where our ninth theory introduces a beautiful and profound extension, a concept called supersymmetry. Supersymmetry, often called SUSY, proposes a deep and elegant symmetry woven into the fabric of reality. For every known particle of matter, like quarks and electrons, and for every force carrier, like photons and gluons, there exists a hidden, heavier twin, a superpartner. An electron would have a selectron, a quark would have a squark, and a photon would have a photino. This doubling of the cosmic cast is not just for mathematical beauty, it solves several fundamental puzzles at once. It offers a path to unifying the forces and provides a perfect candidate for the mysterious dark matter that binds galaxies together. In the high-energy frenzy immediately after cosmic inflation, when the universe was a cauldron of extreme energy, these superpartners would have been produced in abundance. They would have danced alongside the familiar particles in the quark-gluon plasma, a hidden layer of reality briefly made manifest. But as the universe expanded and cooled, a critical shift occurred. Supersymmetry is a broken symmetry, meaning that while the laws of physics respect it, the low-energy world we inhabit does not, the superpartners, being much heavier, rapidly decayed into lighter particles. All of them except one, the lightest supersymmetric particle, the LSB, would have no lighter superpartner to decay into. It would be absolutely stable, a frozen relic from that first fiery instant. This particle, forever drifting through the cosmos, unable to interact with light or ordinary matter except through gravity, fits the description of dark matter perfectly. One of the prime candidates for this role is the gravitino, the hypothetical superpartner of the graviton, the particle that would carry the force of gravity. If the gravitino is the lightest superpartner, then it would have been forged in the earliest moments and survived untouched for billions of years. In this view, the dark matter that now shapes the cosmos is not some exotic afterthought. It is a direct descendant of the universe's first particles, a shadow population of superpartners that has been with us since the beginning. The hunt for these particles at places like the Large Hadron Collider is in essence an archaeological dig into the first trillionth of a second of time, searching for the hidden twins of our familiar world. But supersymmetry is not the only path to the dark heart of the cosmos. Another ghostly candidate emerges from a different puzzle entirely, one rooted in the strange behavior of the strong nuclear force. This is the theory of actions, particles so light and shy they could be the universe's first and darkest inhabitants. Their story begins not with cosmology, but with a fine-tuning problem in the equations of quantum chromodynamics, the theory of quarks and gluons. These equations allowed for a type of symmetry violation that should make the neutron have a much larger electric dipole moment, a slight imbalance in its charge distribution. Experiments show the neutron is exquisitely symmetric, so this violation must be tuned to almost zero. To explain this unnatural cancellation, physicists proposed a new field that would naturally suppress this effect. The quanta of this field are the actions, named after a laundry detergent for their ability to clean up the problem. These particles are theorized to be incredibly light, billions of times lighter than an electron, and they interact with ordinary matter only extremely weakly, slipping through planets and people as if they were not there. Because of these properties, actions would have been produced in staggering numbers in the hot early universe, not as fiery collisions, but through a process like a phase transition, condensing out of the cooling cosmic energy like a silent mist. Here is where the idea becomes truly captivating. As the universe expanded, this vast sea of ultralight actions would have undergone a profound transformation. Their quantum wave-like nature, combined with their sheer density, would have caused them to all fall into the same quantum state, forming what is known as a Bose-Einstein condensate. This is not a gas or a liquid, but a single, coherent quantum entity that stretches across cosmic scales. In this view, dark matter is not a swarm of discrete particles whizzing through space. It is a single, immense, and incredibly cold quantum wave, a ghostly medium that permeates every galaxy. This action condensate could have been one of the very first coherent structures to form in the universe, a smooth, oscillating field that predated even the first clumps of ordinary matter. Its gentle gravitational pull would have provided the scaffolding upon which hydrogen and helium could later gather, seeding the galaxies we see today. So the action offers a dual legacy. It solves a deep mystery in particle physics and simultaneously paints a picture of dark matter as a primordial quantum atmosphere, a whisper from the first moments that still echoes in the void of space. Our story of first particles has been a tale of quarks and fields, but what if we have been looking in the wrong place entirely? A radical hypothesis suggests the first objects were not particles at all, but tiny, dense knots of pure gravity. These are primordial black holes, and they could rewrite the opening chapter of our cosmic history. According to this idea, in the first chaotic second after the Big Bang, the universe was not perfectly smooth. It was rippling with intense density variations, the same quantum fluctuations that seeded galaxies. In most regions, these wrinkles smoothed out as the cosmos expanded. But in the most extreme pockets where matter and energy were packed together with incredible density, something different happened. Gravity won instantly. Instead of expanding with the rest of the universe, these ultra-dense patches collapsed directly under their own immense weight, punching straight through the formation of particles and pinching off into black holes. This could have happened long before the first protons and neutrons ever had a chance to form. The scale of these objects is mind-bending. They would not be the stellar mass black holes born from dying stars. Primordial black holes could be almost any size, from microscopic specks with the mass of a mountain to colossal entities heavier than 1,000 suns. Some theories even suggest ones as light as an asteroid, smaller than a grapefruit yet containing all that mass. Think of a single, incredibly dense grain of cosmic sand with the gravitational pull of an entire world. These objects would be a fundamentally different kind of primordial relic. They are not a particle in any standard sense, but a topological defect in spacetime itself, a frozen imprint of the universe's most violent infancy. And this leads to their most provocative role. These ancient black holes, drifting unseen through the cosmos for billions of years, are a perfect candidate for dark matter. They do not emit light, they interact only through gravity, and they could be everywhere, weaving the invisible web that holds galaxies together. If they are numerous enough, the universe's first true structures were not clouds of gas, but swarms of these dark gravitational seeds. The hunt for them is on, with astronomers looking for the occasional telltale flash as one passes in front of a distant star, briefly magnifying its light, or for the ripples they might leave in the cosmic microwave background. It is a breathtaking possibility that the dominant substance of our cosmos might not be an exotic particle, but a population of fossilized cosmic pinpricks, the first and darkest children of creation. Black holes are gravitational fossils, but other relics might be hiding in the cosmic background, remnants of a time when the universe's forces were one. This brings us to a profound prediction from grand unified theories, the magnetic monopole. To understand this, we must step back to a fraction of a second after the beginning, to an era of unimaginable energy called the GUT epoch. Grand unified theories propose that the three non-gravitational forces, the electromagnetic, weak, and strong nuclear forces, were not always separate. They were once facets of a single, majestic superforce. In that unified state, the particles we know would have been indistinguishable from one another, part of a simpler, more symmetric reality. As the universe expanded and cooled past a critical temperature, this perfect symmetry broke. Think of it like water freezing into ice crystals. The water is uniform, but as it freezes, it picks a specific crystal structure, locking in a pattern. Similarly, as the cosmos cooled, the single force fractured into the three distinct forces we see today. This phase transition, however, would have left behind defects in the fabric of reality, just as freezing water can trap air bubbles or cracks in the ice. And one of the most dramatic of these defects would be the magnetic monopole. In our everyday world, magnets always come with two poles, a north and a south. Cut a bar magnet in half and you get two smaller magnets, each with its own north and south. A magnetic monopole defies this completely. It is a particle that carries only a single magnetic charge, either a north pole alone or a south pole alone. It would be a fundamental magnetic particle, just as an electron is a fundamental electric charge. According to grand unified theories, these monstrous particles would have been produced in abundance during that early symmetry-breaking moment. They would be incredibly heavy, perhaps as massive as a bacterium but compressed into a subatomic size, making them among the most massive elementary particles conceivable. And they would be virtually indestructible, stable relics that should have survived from that first second to the present day. Herein lies the crisis, the monopole problem. If grand unified theories are correct and the universe cooled slowly and uniformly, calculations show these monopoles should be everywhere, as common as protons. Their immense mass would have dominated the density of the universe, overwhelming everything else and causing it to collapse long before galaxies could ever form. The fact that we exist and that no one has ever definitively found a magnetic monopole presented a devastating contradiction. This glaring problem was one of the key motivations for the theory of cosmic inflation. That brief period of hyper-expansion would have stretched the universe so dramatically that it would have diluted the monopoles to near invisibility, scattering them so far apart that you might find only one in our entire observable universe. So the magnetic monopole stands as a ghostly testament to unity, a particle that should exist, whose absence helped shape our understanding of the cosmos's very first moments. While monopoles are ghosts of a broken symmetry, another theory reimagines the Big Bang itself, not as an explosion from a point, but as a shattering impact in a hidden dimension. This is the ekpyrotic universe, a model where our entire cosmos exists as a three-dimensional membrane or brain, adrift in a higher dimensional space. Picture our reality not as an island, but as a vast flat sheet, one of many floating in an unseen ocean. In this view, the Big Bang was not the beginning of time and space, but a violent, transformative event. It was the moment our brain collided with another parallel brain in that higher dimensional realm. The name ekpyrotic comes from the ancient Greek for conflagration, a great fire born from a clash. Imagine two enormous sheets of reality, slowly drawn together by gravity across the bulk, the space between dimensions. They do not simply bump, they scrape and resonate, transferring an immense tidal force of energy across their entire surfaces. That energy, concentrated into our three-dimensional sheet, became the searing hot, dense state we recognize as the beginning of our cosmic expansion. The first particles in this story were not born from a singularity's decay, but from the shock waves of a cosmic collision. As the brains rebounded from each other, the energy of their impact would have rippled across our brain, exciting every quantum field at once. This would generate a flood of particles in a state of thermal equilibrium, a hot soup remarkably similar to the one described by the standard Big Bang, but with a profoundly different origin story. The initial conditions for our universe, its uniformity and the pattern of its primordial wrinkles, would not be set by a period of inflation, but by the precise way the brains interacted, their texture, their angle, and the dynamics of their collision in the higher dimensional bulk. It is a cyclical vision where brains might oscillate, collide, and separate over eons, each collision birthing a new cosmic epoch from the ashes of the last. In this model, we are living in the aftermath of a crash, and the first particles were the sparks thrown from that unimaginable collision of worlds. The idea of a cosmic collision reshapes our origin, but what if the story has no beginning and no end? Roger Penrose offers a vision of eternity with his theory of conformal cyclic cosmology, a model where the universe is reborn not from a crash, but from a profound transformation at the edge of time. Penrose asks us to consider the far, far future when all stars have burned out, all black holes have evaporated, and all particles have decayed into their lightest forms. In this state of maximum entropy, the universe is a cold, dark, and nearly empty expanse, expanding forever into an endless, featureless void. At this extreme, something remarkable happens mathematically. The vast scales of space and time lose all meaning. With no stars to measure distance and no events to mark time, the geometry of this endless future becomes mathematically identical or conformally equivalent to the hot, dense, ultra-small geometry of a Big Bang singularity. In this breathtaking symmetry, the end of one cosmic cycle becomes the beginning of the next. The universe does not bounce, it resets. One eon, as Penrose calls a full cycle from Big Bang to eternal expansion, gives way seamlessly to the next eon in an infinite chain without a first or final link. So what seeds this new beginning? In this model, the very first particles of a new eon are not born from nothing. They are the ultimate recycled materials. As the previous eon drew to a close, the last structures to vanish would be the supermassive black holes, slowly leaking their mass away through Hawking radiation over unimaginable eons. In their final moments, these titans would erupt in a burst of energy. According to Penrose, that energy, those evaporated particles, do not simply dissipate into the void. Instead, they are infinitely stretched and blue-shifted as the eon ends, their information and energy carried across the conformal boundary to become the initial seeds of the next eon's hot, dense state. This process might leave a ghostly fingerprint on our sky. Penrose and his colleagues suggest that the concentrated bursts of radiation from those dying black holes could imprint as faint, circular rings of elevated temperature in the cosmic microwave background, the afterglow of our own Big Bang. These are called Hawking points, and they would be windows looking not just into our past, but into the eon that came before ours. If they are real, the first particles that sparked our entire cosmos were the last size of giants from a previous universe, their final breath becoming our first light. The universe's first particles may not be fundamental at all, but a grand cosmic illusion. This is the staggering implication of the holographic principle, a theory that reshapes our understanding of reality itself. The idea emerged from the study of black holes and a deep puzzle about information. When matter falls into a black hole, it vanishes from our universe, seemingly erasing all information about what fell in. This violates a core tenet of quantum mechanics, which states information can never be truly destroyed. To resolve this paradox, physicists like Jacob Bekenstein and Stephen Hawking propose that a black hole's entropy, a measure of its hidden information, is not proportional to its volume, but to the surface area of its event horizon. All the data describing everything inside the black hole is somehow encoded on its two-dimensional boundary. The universe then might work the same way. The holographic principle suggests that everything we perceive in our three-dimensional world, every galaxy, every planet, every atom in your hand, could be a projection of information stored on a distant, two-dimensional surface that encloses us. Think of a credit card hologram. The flat, shiny sticker contains all the data needed to project a three-dimensional image that seems to have depth and volume. In a cosmic sense, we might be living inside that projected image. Apply this mind-bending logic to the universe's first moments. In the extreme density just after the Big Bang, the entire nascent cosmos could have been describable as a quantum system on its own boundary, a flickering, two-dimensional screen of ultimate information. On that screen, the laws of physics would be simpler, perhaps written in the language of quantum bits or qubits, without any notion of space or particles as we know them. As this system evolved, the information on the boundary became so complex that it effectively projected the illusion of a third spatial dimension, along with all the particles and forces within it. In this view, the first particles, like quarks and electrons, were not the primary ingredients. They were emergent phenomena, like pixels lighting up on a vast screen to create the convincing movie of a three-dimensional world. The heat of the quark-gluon plasma, the binding of protons, the very fabric of spacetime, all become secondary features of a deeper, information-theoretic reality. So if the holographic principle is true, we are not just asking what the first particles were, but what the first bits of cosmic information were, and what kind of code the universe used to write itself into existence. That ghostly sea of neutrinos is flowing through you right now. Among the first particles to break free from the cosmic fire, they carry a whisper from a universe just 1 second old. In that first frantic second, the universe was still a dense, opaque plasma of particles, constantly colliding and interacting. Neutrinos, however, are the ultimate introverts of the particle world. They are almost massless, carry no electric charge, and interact only via the weak nuclear force and gravity, making them incredibly slippery. About 1 second after the Big Bang, as the cosmos expanded and cooled to roughly 10 billion degrees, something critical happened. The density and energy dropped to a point where neutrinos could no longer find other particles to bump into. They simply stopped interacting, flying free into the expanding void. This moment is called neutrino decoupling. In an instant, the universe became transparent to these elusive particles, while the rest of matter remained trapped in a blinding soup for hundreds of thousands of years longer. When these neutrinos decoupled, they were moving at nearly the speed of light, carrying with them a perfect imprint of the conditions at that exact moment, frozen in time. As the universe continued to expand, these trillions upon trillions of particles were stretched and cooled, forming a pervasive cosmic sea known as the cosmic neutrino background. It is the older, quieter sibling to the more famous cosmic microwave background, which came much later. This background is not a faint echo, it is a present and overwhelming reality. Scientists estimate there are about 300 of these relic neutrinos in every single cubic centimeter of space, meaning trillions pass through your body every second without a trace. They are the universe's first free travelers, cosmic voyagers that have been journeying unimpeded for almost 14 billion years. Detecting them, however, is one of the greatest experimental challenges in all of physics. Because they interact so rarely, catching one is like trying to hear a single whispered word in a hurricane. Our current detectors are built to catch the more energetic neutrinos streaming from the sun or distant supernova, but the relic neutrinos from the Big Bang have been cooled to a temperature just a fraction of a degree above absolute zero, possessing almost no energy at all. To find them, we would need a detector of unimaginable scale and sensitivity, perhaps using a vast volume of ultra-pure material, waiting for the once-in-an-era event where a relic neutrino finally, miraculously, bumps into an atomic nucleus. Success would give us something priceless, a direct snapshot of the infant universe at the tender age of 1 second, a look into the forge of creation long before the first atoms ever formed. The neutrinos slipped away into the dark, leaving the universe still blindingly bright and opaque. For nearly 400,000 years, the cosmos remained a seething, ionized plasma, a fog of charged particles where light was perpetually trapped. A photon, a particle of light, could not travel more than a tiny fraction of an inch before being violently scattered by a free electron, bouncing endlessly in a prison of its own making. This was the state of everything until the universe cooled to a critical threshold of about 3,000 degrees. At that temperature, something monumental happened, an event physicists call recombination, though nothing is truly combining for a second time. It was the moment the cosmos became transparent. As the expanding universe cooled, the frantic electrons finally lost enough energy to be captured by the roving protons. They settled into orbit, forming the first stable, neutral atoms, overwhelmingly of hydrogen. This process cleared the fog. With most of the free electrons suddenly locked away inside atoms, the photons had a clear path. For the first time in cosmic history, light could travel in a straight line. The universe, in an instant, went from an opaque, glowing soup to a transparent, dark expanse, punctuated by this sudden flash of liberated light. Those first free-streaming photons, bursting forth from the last scattering surface, are what we detect today as the cosmic microwave background. It is not a flash from the Big Bang itself, but from the moment the universe took its first breath, when matter settled into its simplest form and let the light shine through. That primordial glow has been traveling for over 13 billion years, stretched and cooled by the relentless expansion of space itself. The microwaves that quietly hiss through every corner of the cosmos, that static on an old television set, are the redshifted afterglow of creation's first dawn. This is our deepest and most precise baby picture of the universe, a snapshot from a time long before the first stars ignited. By mapping its minute temperature variations, its faint ripples and whispers, cosmologists can read the blueprint of the future, seeing the gravitational seeds that would one day grow into galaxies and clusters. The cosmic microwave background is the ultimate fossil, the tangible echo of a time when everything was simple, smooth, and finally filled with light. Our cosmic story has been built on a foundation of quarks and electrons, but what if these are not the end of the line? To find a deeper layer of reality, we must journey to a speculative frontier where the smallest known particles are not fundamental at all. This is the theory of prions, a bold idea that proposes quarks and leptons are themselves composite, built from something even more basic. In this view, the familiar cast of the Standard Model, from the up quark to the electron neutrino, are not elementary. They are like atoms made of smaller constituents bound together by a new, ultra-powerful force. These hypothetical building blocks are called prions, a name simply meaning before. If this model is correct, then in the fiery aftermath of the Big Bang, the first true particles to condense from the energy of creation were not quarks and gluons, but prions and their force-carrying partners. Imagine the quark-gluon plasma not as a soup of fundamental dots, but as a churning sea of these tinier entities, already binding and rebinding in the extreme heat. As the universe cooled further, this new prionic force would have confined them, permanently locking prions together in specific combinations to form the quarks and electrons that would go on to build our world. Why propose such a layer of complexity? One of the most compelling motivations is to explain a puzzling pattern in nature, the generational structure of matter. We have three nearly identical families of particles. The first generation gives us the up and down quarks that make protons and neutrons, along with the electron and its neutrino. These are the stable particles of our everyday world. Then, for reasons unknown, the universe created two more generations, carbon copies that are progressively heavier and wildly unstable, like the charm and strange quarks and the muon. The Standard Model treats these generations as fundamental facts, but offers no explanation for why they repeat or why there are exactly three. A prion model suggests a beautiful economy. Perhaps all these different quarks and leptons are just different combinations of just a few types of prions, arranged in different ways, much like how protons and neutrons are different combinations of just two types of quarks. The three generations could then arise naturally from the different possible configurations these prionic building blocks can take. In this speculative vision, the first particles were the ultimate Lego bricks, and the entire zoo of matter we see today is the intricate but finite set of structures that could be built from them in the universe's first moments. That cosmic neutrino sea is a relic of particles we understand, however strange they may be. But what if the early universe produced something even more bizarre, entities that defy the very definition of a particle? This is the radical proposal of unparticle physics, a theory from physicist Howard Georgi that suggests a hidden sector of reality operating by utterly different rules. In our familiar world, particles have specific properties, most notably a definite mass. An electron or a quark has a mass you can measure, which dictates how it moves and interacts. Unparticle stuff, in stark contrast, has no fixed mass scale at all. Instead, it exhibits scale invariance, meaning it looks the same at all energy levels. Think of a fractal coastline where the pattern of bays and peninsulas repeats whether you view it from an airplane or through a magnifying glass. Unparticle stuff would behave similarly, lacking a single defining characteristic, size or energy. In the extreme energies of the early universe, our known particles could have interacted with this hidden sector. Through a process Georgi called dimensional transmutation, the high-energy symmetry between the sectors would break, leaving behind this scale-invariant unparticle stuff as a cosmic residue. What would this substance be like? It would not clump into atoms or form neat beams. It would be a diffuse, wispy medium with properties somewhere between a particle and a continuous field. Its influence would be ghostly but profound. Because it does not have a specific mass, it would not behave like cold dark matter, sitting still in galactic halos. Instead, it could act as a form of dark radiation, streaming through the cosmos and subtly altering how structures form. The imprint of such an exotic component might be found in the delicate details of the cosmic microwave background, in the precise way its temperature variations are distributed, or in the timing of when the first galaxies assembled. Searching for unparticle physics is not about finding a new particle in a collider. It is about detecting the faint, statistical whisper of a reality that plays by an entirely different set of rules, a hidden layer of creation that never crystallized into the familiar forms we know. Our universe is haunted by two separate phantoms, dark matter and dark energy, but what if they are just two faces of the same, deeper mystery? A bold class of cosmological models proposes exactly that, suggesting a single, exotic substance that unified the cosmos from the very start. This is the idea of a unified dark fluid, with one of its most famous candidates being the Chaplygin gas. Named after a Russian physicist who studied aerodynamics, this hypothetical fluid has a truly bizarre property. Its pressure is negative and inversely proportional to its density. In simpler terms, as the universe expands and this fluid becomes less dense, its negative pressure grows stronger, acting like a repulsive force. This single behavior elegantly explains two cosmic eras. In the early, dense universe, the Chaplygin gas would have behaved just like cold dark matter, clumping under gravity to form the scaffolding for galaxies. Its pressure was negligible, so it acted like a collisionless, gravitating dust. But as expansion continued and the fluid thinned out, its negative pressure began to dominate. It transitioned smoothly from pulling matter together to pushing space itself apart, driving the accelerated expansion we attribute to dark energy. In this view, the dark sector is not a zoo of different entities, but a single, evolving essence that has guided the cosmos from infancy to old age. So what would be the first particles in such a universe? They would not be independent specks of matter. Instead, the fundamental excitations, the quanta, would be ripples or waves within this all-pervading, unified dark fluid. From the first moments after inflation, this fluid would have been the dominant component of reality, its strange quantum fluctuations setting the rhythm for everything that followed. Ordinary matter, the protons, neutrons, and electrons that make up our world, would be a mere afterthought, a slight perturbation floating on this vast, dark ocean. The Chaplygin gas model offers a stunning simplification, turning two of cosmology's greatest puzzles into one. Yet it faces challenges, particularly in explaining the detailed clustering of galaxies we observe, which seems to prefer the separation of dark matter and dark energy into distinct components. Still, it stands as a powerful reminder that our deepest answers may lie not in adding more pieces to the puzzle, but in realizing that some pieces we thought were separate are in fact part of the same whole. Our universe may be built not from particles but from a single, profound question. The spinor theory of everything proposes that the fundamental substance of reality is not matter, not energy, not even space-time, but a mathematical object of exquisite complexity called a spinor field. To grasp this, forget everything you picture as a building block. A spinor is not a tiny dot nor a vibrating string. It is a more abstract entity, a mathematical description of intrinsic rotation, a quantum state that requires a full 720-degree turn to return to its starting point, not the 360 degrees we are used to. In this radical vision, before there were quarks, before there were dimensions, there was only this primordial, all-encompassing spinor field, a cosmic ocean of potential rotation. The dynamics of this field, its ripples and knots, would give rise to everything we perceive. Think of it like this: imagine a perfectly calm lake. That smooth surface represents the pure spinor field in its ground state. Now disturb that surface with a specific, stable pattern of whirlpools and intersecting waves. One particular, self-reinstanding whirlpool configuration might manifest in our reality as an electron, its charge and mass arising not from internal parts, but from the precise topological shape of the spinor knot. Another, more complex stable knot might be a quark. Even space-time itself, the very stage upon which particles move, would not be a pre-existing container. It would emerge as a collective property of the spinor field's behavior, much like the temperature of a gas emerges from the collective motion of its molecules, not from any single atom. In this view, the first particles were solitons, self-sustaining twists in the fabric of the spinor field that refused to smooth themselves out. They were not born from collisions in a hot plasma, but crystallized from the cooling of this fundamental field as the universe expanded, like intricate ice formations freezing in a particular pattern. Their properties, their very identities, are locked into their geometry. This offers a breathtaking unification where matter, forces, and the geometry of the cosmos all share a single, elegant origin, a universe written in the language of quantum rotation. That mathematical ocean of spinors is a vision of ultimate continuity, but what if the true foundation of reality is not continuous at all? Causal set theory offers a profoundly different answer, one where the universe is built not from a smooth fabric, but from a discrete, growing network of pure cause and effect. This approach to quantum gravity proposes that spacetime is not fundamental. Instead, what is truly real is a collection of discrete events like individual points, with a single, simple rule connecting them, a partial order that tells you which events can influence which others. This structure is called a causal set. Think of it as the universe's most basic ledger, a list of every single happening with arrows drawn only from causes to their direct effects. The smooth, four-dimensional spacetime we experience, with its distances and geometry, is an illusion that emerges when you look at this vast network from a distance, much like a photograph emerges from the discrete pattern of pixels on a screen. In this view, the history of the universe is not a pre-existing timeline. It is a causal set that is continually growing, with new events being added at the forefront of time. Each new event must have a cause or a set of causes already within the existing network. So what then are the first particles in such a universe? They cannot be little balls moving through a pre-existing space. Instead, a particle like an electron would be a specific, persistent pattern within the causal set, a stable chain or a cluster of events whose internal causal relationships repeat in a recognizable way. Its properties, its mass, its charge, even its location, are not intrinsic labels. They are defined entirely by how that particular pattern of events connects to the rest of the network. An electron here versus an electron, there would simply be two identical patterns anchored to different parts of the causal web. This makes creation a deeply relational process. A particle does not exist in isolation. It is a knot of causality, a story told by the specific way a set of events influences and is influenced by the rest of reality. The very first particles to crystallize would have been the simplest stable patterns that could form as the causal set began its growth from a primordial seed. They would be the elementary stories from which all more complex narratives, from atoms to galaxies, would eventually be composed. It is a universe where existence itself is a tapestry of relationships, woven one causal connection at a time. The causal set paints a universe of pure relationship, but another theory proposes our entire reality is a consequence of a single, cataclysmic relationship with a parent cosmos. This is the black hole universe hypothesis, a mind-warping idea that suggests we are living inside a black hole. In this view, our Big Bang was not the ultimate beginning. It was the moment a massive star or another dense object in a larger parent universe collapsed inward past its event horizon. From the outside, that collapse would end in a singularity, a point of infinite density. But from the inside, the story is utterly different. An observer falling into that black hole would not see a singularity ahead, but would experience something akin to a Big Bang. As they cross the horizon, the geometry of spacetime undergoes a radical transformation. The direction that was toward the center outside becomes the direction of future time inside. The singularity is not a place in space you hit, it is a moment in time, the end of time for everything within. So the entire history of our universe, from the hot dense state to the present day, could be the interior evolution of a black hole born in another reality. This flips our perspective completely. The cosmic microwave background, the relic glow of our hot beginning, would not be the aftermath of a primordial explosion from a point. It would be the thermalized energy of the event horizon itself, translated inward. The first particles in our cosmos, the seething quark-gluon plasma, would be the quantum gravitational processes at that boundary, made manifest within. This is where the holographic principle becomes essential. All the information describing everything that fell into the black hole, every atom of the progenitor star and anything else it swallowed, is encoded on its two-dimensional event horizon. The three-dimensional universe we experience, with its galaxies and particles, is a holographic projection of that data. The intense heat and density of our early universe are not the cause, but the effect of that information being processed and projected inward. Imagine the horizon as a vast, vibrating membrane buzzing with quantum bits. The specific patterns of those vibrations get translated via the laws of quantum gravity into the particles and forces that fill our interior space. A particular quantum fluctuation on the horizon might project inward as a quark-antiquark pair appearing in the early plasma. The uniformity of the cosmic microwave background reflects the thermal equilibrium of the horizon, while the tiny ripples in it correspond to quantum jitters on that boundary surface. In this breathtaking synthesis, the first particles were not independent entities, but holographic echoes of a boundary process, the interior reflection of a firewall of information. This idea even offers a potential explanation for the universe's expansion. As the parent black hole continues to accrete matter from its external universe, its mass grows and its event horizon area increases. Translated to our interior perspective, that growth of the horizon could be what we perceive as the ongoing expansion of space itself. We are not in an isolated bubble, but in a dynamic entity still connected to a greater cosmos, its growth driving our own. It is a cosmic Russian doll model where every black hole may contain a universe, and our own universe may itself be filled with black holes, each potentially birthing its own nested cosmos in an infinite fractal chain of creation. Gravity is the force we know best, the pull that grounds us to Earth and guides the planets in their orbits. But what if this familiar force is not fundamental at all, but a side effect, a collective illusion born from something deeper? This is the radical proposal of emergent gravity, a theory championed by physicist Eric Verland. It suggests gravity is not a basic ingredient of the cosmos, but an entropic force, a phenomenon that arises from the natural tendency of systems to move toward disorder, much like the way heat flows from a hot object to a cold one. To grasp this, picture a stretched rubber band. When you let it go, it snaps back to its relaxed state, not because of a fundamental snapping force, but because that relaxed state is statistically more likely. It has higher entropy. Verland proposes that gravity works in a similar statistical way, emerging from the behavior of the most fundamental stuff of reality, information. This idea builds directly on the holographic principle, where our three-dimensional universe is a projection from a two-dimensional surface containing quantum bits of data. In this view, what we perceive as empty space is actually a vast, dynamic holographic screen teeming with these microscopic information bits. When a mass, like a star or a planet, is present, it effectively cools a region of this screen, lowering the entropy of the information there. Nature, seeking to maximize entropy again, responds by pushing more information bits into that cooler region. This statistical push to restore balance manifests as what we feel as gravity. The planet does not attract you with a mysterious force. The universe is simply reorganizing its information in the most probable way, and you get carried along for the ride. Apply this breathtaking logic to the universe's first moments. There were no separate particles and no pre-existing stage of spacetime. Instead, the cosmos began as a dynamic, pre-geometric network of information exchanges, a churning sea of quantum data. As this system evolved, seeking higher entropy configurations, stable patterns began to crystallize from the noise. These were not particles moving through space. They were coherent bundles of information whose very existence defined their location and momentum. Spacetime itself, the concepts of here and there, emerged alongside them as the geometry of their relationships. In this co-evolution, what we call a quark and the space it occupied were born together, two facets of the same informational process. Gravity did not switch on as a separate force. It was the thermodynamic consequence of this entire system's drive toward equilibrium. The statistical gradient that appeared as the information structure grew more complex. So the first particles were not things being pulled by gravity. They were the very disturbances in the informational fabric whose collective behavior would later be interpreted as a gravitational force. This turns our origin story inside out, suggesting the cosmos began not with a forceful bang, but with a quiet computation, a rearrangement of cosmic data whose most noticeable side effect was the gentle, persistent pull we have always known. Gravity might emerge from information, but information itself requires a mind to interpret it. This leads us to one of the strangest and most unsettling ideas in all of cosmology, the Boltzmann brain paradox. Named for the physicist Ludwig Boltzmann, this is not a theory of first particles, but a devastating critique of our assumptions about the universe's initial state and our place within it. Boltzmann worked on thermodynamics, exploring how systems evolve from order to disorder. He realized that in a truly random system, even the most ordered state could, by sheer chance, spontaneously appear as a random fluctuation. Given enough time, a tornado sweeping through a junkyard could, by accident, assemble a perfectly functioning jet engine. The Boltzmann brain takes this to its ultimate, bizarre conclusion. In an eternally expanding universe, or one that exists for an unimaginably long time, the random jostling of particles in the void could, by pure accident, momentarily assemble a fully formed, conscious human brain, complete with all its memories and sensations of a past that never actually happened. This brain would flicker into existence, believe itself to be a person living in a real world, and then, in the next instant, dissolve back into chaos. The paradox arises when we apply this to modern cosmology. In many models of eternal inflation or a cosmos with a cosmological constant, the universe is destined to expand forever, approaching a cold, empty state of maximum entropy called heat death. But in such an eternal, nearly featureless void, random thermal fluctuations become the only game in town. Given infinite time, these fluctuations will produce every possible configuration of particles, no matter how unlikely. The math suggests a horrifying result. The number of these fleeting, self-aware Boltzmann brains produced by random chance would eventually become astronomically larger than the number of ordinary observers like us, who evolved gradually within an ordered universe over billions of years. So if you are a conscious being pondering the cosmos, you are statistically far more likely to be a momentary accident in the void than a product of a long, structured cosmic history. This is the paradox. It forces us to confront a terrifying question about our own reality. Are we the legitimate outcome of a universe with a very specific, low-entropy beginning, or are we just a fleeting statistical glitch? For cosmologists, this is not a philosophical game. It is a serious constraint. Any theory of the universe's first particles and initial conditions must produce a cosmos where ordinary observers reliably outnumber these random phantom minds. If a model predicts we should be Boltzmann brains, that model is likely wrong. The paradox forces us to refine our ideas about inflation, the cosmological constant, and the very arrow of time, pushing us toward theories that genuinely explain why the universe started in such an exquisitely ordered state, making our existence not a random accident but an expected outcome. The idea that we might be living inside a simulation is no longer just science fiction. The simulation hypothesis, popularized by figures like Nick Bostrom, proposes a staggering possibility. What if our entire cosmos, with all its galaxies, forces, and particles, is not a fundamental reality, but a complex simulation running on a computer of unimaginable power in some other, base-level universe? From a cosmological perspective, this flips the entire quest for first particles on its head. If we are in a simulation, then the fundamental layer of our reality is not physical. It is informational. The quarks, electrons, and photons we have been discussing are not the bedrock. They are high-level representations, the rendered graphics of a deeper computational process. The true first particles of our universe would be the initial bits, or more likely quantum bits, qubits, that were loaded into the simulation's memory when the program booted up. Our Big Bang was not a physical explosion, but the initialization of this cosmic computer, the moment the simulation's runtime began and the starting variables were set. In this view, the laws of physics we have painstakingly uncovered are not fundamental truths of nature. They are the algorithms, the elegant and efficient code that governs how this digital substrate evolves over time. The conservation of energy and momentum are like error-checking routines ensuring the simulation runs stably. The speed of light is a processing speed limit, a constraint on how quickly information can propagate across the simulation's grid. Even the strange results of quantum mechanics, like superposition and entanglement, could be artifacts of an underlying quantum computer architecture where qubits can exist in multiple states at once. This idea, sometimes called digital physics, suggests that at the smallest scales, spacetime itself has a discrete, pixelated structure, a fundamental Planck-length resolution that hints at the underlying computational lattice. The hunt for the first particles, then, becomes a search for the source code of reality. The uniformity of the cosmic microwave background might reflect a well-optimized initial condition. The mysterious fine-tuning of constants could be the carefully chosen parameters set by the programmers to allow for complex structures like stars and life to emerge. While this hypothesis is currently untestable in any conventional sense and dwells in the realm of philosophy as much as physics, it forces a profound shift in perspective. It asks us to consider that the universe's deepest truth may not be written in the language of mathematics, but in the logic of computation, and that we are not just stardust, but perhaps something even stranger, living data in an ancient calculation. But if our reality is a simulation, who is the programmer? This question leads us back to a profound historical idea that rejected the notion of a beginning entirely. For decades, the Big Bang had a formidable rival, the steady-state theory. Proposed by Hermann Bondi, Thomas Gold, and Fred Hoyle, it offered a radically different vision, a universe with no origin and no end. In this model, the cosmos has always existed and will always exist, looking roughly the same on the largest scales at any point in time forever. This presented an elegant solution to a philosophical unease. Why should there be a single, special moment of creation? But the steady state faced a major obstacle, the observed expansion of the universe discovered by Edwin Hubble. If galaxies are flying apart, the density of matter should be decreasing over time, making the past different from the present. To preserve perfect uniformity, the theory proposed a bold and ingenious mechanism, continuous creation. As the universe expands, new matter is spontaneously created from nothing, just enough to fill the voids and maintain a constant average density. The proposed rate was vanishingly small, about 1 hydrogen atom per cubic meter every few billion years, far too subtle for any experiment to detect directly. This matter would arise not from a fiery singularity, but from a hypothetical background field called the C field, with the C standing for creation. In this timeless cosmos, the very question of the first particle loses its meaning. There are no first particles in a temporal sense, only an eternal, ongoing process of genesis. New hydrogen atoms are constantly popping into existence in the vast, empty spaces between galaxies, providing the raw fuel for new stars to form as old ones die in an endless, self-renewing cycle. The universe has no birthday. It is an immortal, breathing entity, always renewing itself. This idea captivated many because it aligned with a classical preference for an eternal, unchanging cosmos. It removed the need for a singular, inexplicable event at time zero. For a while, the debate raged: Big Bang versus steady state. The discovery of the cosmic microwave background in 1965 proved decisive. That faint, all-pervasive glow was the predicted cooled remnant of a hot, dense past, a relic the steady state could not easily explain without ad hoc adjustments. While it faded as the dominant model, the steady-state theory remains a monumental chapter in our quest. It challenges us to ask if our need for a beginning is a limitation of our imagination, and whether the universe might yet hold the possibility of eternal renewal, where creation is not a one-time event but a quiet, constant whisper in the dark. Gravity may be the dominant force in our cosmic models, but there is a current of thought that suggests we have been profoundly underestimating the sky. The plasma universe, or electric cosmology, offers a vision where the primary sculptor of the cosmos is not gravity, but electromagnetism. In this alternative framework, the universe is not mostly empty space dotted with islands of matter. It is a vast, dynamic sea of plasma, an ionized gas where electrons have been stripped from their atoms, allowing electric currents to flow across cosmic distances. Proponents of this view argue that 99% of the visible universe is in this plasma state, from the wispy filaments between galaxies to the hearts of stars themselves. Here, the immense magnetic fields and powerful electric currents coursing through this conductive medium are the true architects shaping galaxies, powering stars, and birthing solar systems in ways that gravity alone cannot explain. This model often rejects the idea of a Big Bang entirely, favoring an eternal, cyclical universe with no singular beginning and no definitive end. Large-scale structures are not formed by the slow, gravitational collapse of dark matter halos, but by the sudden, sculpting force of cosmic-scale electrical discharges. One of the key mechanisms is called a Z-pinch. Imagine a colossal, intergalactic lightning bolt, a filament of electric current flowing through the plasma. This current generates its own powerful magnetic field, which then acts to pinch and constrict the filament itself, much like squeezing a garden hose. This magnetic pinch can compress plasma with tremendous force, heating it to extreme temperatures and causing it to twist into the familiar shapes of spiral galaxies, or to knot into bright stars along its length. In this local, dynamic sense, the first particles of a new galaxy or star might not be hydrogen atoms quietly gathering, but the electrons and ions caught in the violent, electromagnetic crucible of a Z-pinch discharge, a stellar forge powered not by gravity but by cosmic electricity. The universe, in this view, is an eternal circuit with energy and matter continuously recycling through these grand electromagnetic processes. While this model remains outside the mainstream, challenged by the overwhelming evidence for the Big Bang and the precise predictions of gravitational cosmology, it serves as a powerful reminder that our understanding of cosmic forces is still evolving. It asks us to look at the swirling arms of a galaxy and see not just a whirlpool of stars, but perhaps the glowing trace of a current that stretches across the void. The sheer diversity of possible origins leads to a profound and unsettling question about our own place in the scheme of things. Why does our universe seem so perfectly tuned for our existence? The forces are balanced on a knife's edge, the particles have just the right properties, and the initial conditions were exquisitely arranged to allow for galaxies, stars, planets, and eventually life. One answer to this riddle of fine-tuning is the anthropic principle, and when combined with the idea of a multiverse, it reshapes our search for the first particles into something deeply personal. The principle itself is simple. We observe the universe to be compatible with our existence as observers, because if it were not, we would not be here to observe it. It sounds almost tautological, but its power becomes clear when we embed it within a grander cosmic architecture. Imagine a vast, perhaps infinite, multiverse. This could arise from the endless bubbling of eternal inflation, where each bubble universe cools with its own random set of physical laws and constants. Or it could be the string theory landscape, a cosmic quilt of 10 to the 500 possible universes, each a different solution to the equations. In this unimaginable ensemble, every possible configuration is realized somewhere. There are universes where gravity is 1 billion times stronger, crushing any structure instantly. Universes where the strong nuclear force fails, so no atoms can ever form. Universes that collapse back on themselves in a flash, or expand so rapidly that matter is forever diluted into a thin, cold haze. In almost all of these cosmic experiments, the story ends quickly and silently. No planets, no chemistry, no life, but in a vanishingly small fraction, the dice roll just right. The numbers align, the forces balance, and the initial particles and conditions allow for a long, complex evolution. We, of course, find ourselves in one of those rare, hospitable outliers. This is the selection effect. Our universe's first particles, the specific quark types, their masses, their charges, the precise strength of the forces that bound them, are not the only possible starting point. They are not a unique necessity dictated by a single theory of everything. They are simply the winning ticket in a cosmic lottery of staggering proportions. The hot quark gluon plasma, the 1 in a billion matter-antimatter asymmetry, the specific pattern of quantum fluctuations, all of it was one possible outcome among countless failures. When we ask what the first particles were, the multiverse answer is, it depends on which universe you are in. In ours, they were the set that allowed this grand story to unfold. The anthropic principle does not explain the mechanism that created those particles, but it reframes the question of why these particles. It suggests that the search for a single, inevitable recipe for creation may be misguided, and that our existence itself is the most important clue we have about the nature of that first moment. We are not just studying the origin of the cosmos, we are a living testament to one particular, and perhaps wildly improbable, version of it. The final frontier in our search may not be a particle or a field, but the very act of looking itself. This brings us to the most metaphysical of all our theories, the idea that consciousness is not a late arriving product of the universe, but its fundamental foundation. This perspective draws inspiration from one of the most puzzling interpretations of quantum mechanics, often associated with physicists like John von Neumann and Eugene Wigner. In the quantum world, a particle does not have a definite property, like a specific position or spin, until it is measured. It exists in a blur of all possible states, a superposition described only by a wave of probability. The mathematics is clear, but what causes this wave to collapse into a single, definite reality? The Copenhagen interpretation says the act of measurement by a classical apparatus does it. But some, like Wigner, pushed further. He argued that the measuring apparatus itself is just a collection of quantum particles, so what finally collapses the wave function must be something outside the physical system entirely, the consciousness of the observer. Extend this logic to the ultimate extreme, and you arrive at a staggering possibility. Perhaps the entire universe began in a state of pure potential, a cosmic wave function of infinite possibilities. For it to become the concrete, classical reality we see around us, it required a primordial act of observation. In this view, the first particles were not things that sparked into existence on their own. They were potentialities that only collapsed into actuality when they were seen. This turns the traditional story of cosmogenesis completely inside out. We are not conscious beings emerging from a dead, mechanical universe. Instead, a foundational consciousness is what breathed fire into the equations, what chose one specific history from an infinite tapestry of might-have-beens. The hot quark-gluon plasma, the first photons, the very fabric of space-time, all became real through an act of witnessing. Who or what could be that first observer? The proposals range from a cosmic mind, a form of universal consciousness inherent to reality itself, to a more philosophical notion where the universe observes itself into being, a self-excited circuit where existence requires perception to complete it. This idea blurs the line between physics and philosophy, between science and metaphysics. It suggests that at the heart of creation lies not a what, but a who, and that our own mindful awareness of the cosmos is not an accident, but a faint echo of that first, foundational act of attention that brought everything into being. We have journeyed across the entire spectrum of cosmic creation, from the silent singularity to the churning quantum foam, from the first free quarks to the last whispers of a previous eon. We have seen the universe as a symphony of vibrating strings, a tapestry of causal connections, and a hologram projected from a distant screen of information. Each theory offers a different lens, a unique story of how something came from the first, unfathomable flicker. The truth is, we may never know with absolute certainty what those original seeds of reality were. The first moments are locked behind a veil of energy so extreme our current physics dissolves into uncertainty. Yet this is not a failure of science, it is its greatest triumph. The relentless pursuit of these 30 theories, from the bedrock of the Big Bang to the wild shores of consciousness-caused collapse, represents humanity's most profound ambition to understand our own origin story. It pushes our mathematics to the brink, forces our experiments to incredible extremes, and challenges our very notions of reality, time, and existence. This quest is more than a technical puzzle. It is a fundamental human yearning to know where we came from and, by extension, who we are. Every new observation of the cosmic microwave background, every collision in a particle accelerator, every refined equation is a step further back toward that initial mystery. So as we look up at the night sky, we are not just seeing points of light, we are gazing at the ultimate legacy of that first cosmic instant, whatever it may have been. Which of these visions of the beginning resonates most deeply with you? Do you believe we will ever find a single, definitive answer, or is the mystery itself the most beautiful part? Share your thoughts in the comments below, and don't forget to subscribe for more deep dives into the mysteries of our cosmos.